All right, so this is a talk about Pauli channels and learning Pauli channels. So a Pauli channel is a special kind of quantum channel that you might think of as a model for noise in a quantum circuit, kind of what happens to your qubits when you do nothing to them. I've drawn a picture here of an example Pauli channel operating on n equals 5 qubits. So such a Pauli channel has a property that with different probabilities, it does different Pauli operators to the qubits. So in this example, when you pass n qubits through the channel, 5 qubits, with 60% chance, it does the identity operator to all of them. So it does nothing. But with 30% chance, it does, an x to the second qubit. And with a 5% chance, it does, z's on the third and fourth qubits, and so forth. Okay, so a Pauli channel operates like this for some choices of Pauli operators and probabilities. Okay, in general, if you have n input qubits, then when the n qubits go through, the channel will apply some Pauli operator on n qubits, which is indexed by a string of i's, x's, y's, and z's of length n. And if we call that sigma, then it does this particular Pauli operator with some probability p of sigma. So p is a probability distribution over strings of i's, x's, y's, and z's. And the goal for this talk is to come up with a methodology for learning this probability distribution P using access to the channel. Okay, so this probability distribution P is defined by 4 to the power of n numbers. So that's a lot of numbers. And if you want to learn this probability distribution in an extremely accurate and stringent way, then you're going to need a really bad dependency on n. So we're going to think of a model of learning which is kind of weak. It's sort of the weakest nice model of what it means to learn this probability distribution. Our goal will be to learn all of the probabilities, p of sigma, up to an additive error of epsilon, where epsilon is a parameter with high probability. And notice that any probability that's smaller than epsilon, we can just output 0 as our estimate for that probability, and that'll be accurate to within plus or minus epsilon. So in some sense, we only have to worry about trying to learn the sigmas that have a pretty large probability, a probability that's bigger than epsilon. And therefore, our algorithm really needs only output at most 1 over epsilon many non-zero estimates, or proportional to 1 over epsilon non-zero estimates. So we can potentially get an algorithm that has even no dependence at all on n. So what's our goal here? Our desire is to learn to this kind of accuracy, estimate all these probabilities up to plus or minus epsilon, while minimizing the number of times we use the channel, and also like the number of states we need to prepare and the number of measurements we do. And in this work, Steve and I really wanted an algorithm that's as simple as possible. So that's another desire. So let me tell you about a pretty simple solution that would be maybe considered the standard solution for this task. And it uses this well-known tool of superdense coding. So let me first illustrate it when it's a 1 qubit channel, when n is 1. So this channel just applies either I, x, y, or z to the qubit with some 4 fixed probabilities, and we're interested in learning those 4 probabilities. Okay, so the standard solution looks like this. What you do is you prepare an EPR pair, or a Bell state, these 2 qubits in this state. And you pass the first qubit through the channel, and you keep the second qubit in your pocket. And it's not too hard to check what happens based on the 4 things that the channel might do. So if the channel, applies the I operator, then nothing changes, and your 2 qubits, when they come out, are still in the Bell state or the EPR pair. Okay, if your channel applies the X, like the NOT gate, to the first qubit, then you get this state, which looks like 1, 0 plus 0, 1. And so forth. Here are the other 2 possibilities if it applies Y and if it applies Z. And so based on the 4 things that could apply, there are 4 different output states for your 2 qubits. And these 4 states are mutually orthogonal, so they're perfectly distinguishable with the 2 qubit measurement. So you can do this 2 qubit measurement, and it basically exactly tells you whether the channel applied I, X, Y, or Z. So in fact, you can do this in general on an n-qubit channel just by separately doing it to all the qubits. So you'll prepare n bell pairs, you'll pass all their halves through the channel, you'll do n 2-qubit measurements, and the upshot is, like, with one use of the channel, you'll sort of exactly see the Pauli string applied by the channel. So you'll exactly sort of determine what string it applied. And now your learning task is completely classical. It's no longer really quantum. It's just like you have access to samples from an unknown probability distribution P on these strings of 4 symbols. And the most obvious natural algorithm, just draw a bunch of samples and output the empirical histogram of what you see. The empirical distribution of what you see is easily shown to work. And it's very standard that with high probability, if you use like 1/epsilon² samples, you'll get the desired result, knowing all the probabilities up to plus or minus epsilon. And that 1/epsilon² many samples are also required for this task. Even to learn a coin flip, which has 2 outcomes rather than 4 to the outcomes, to the bias of a coin flip to additive accuracy epsilon, you need 1/epsilon² samples. Okay, so this algorithm has optimal sample complexity. And it has other pros too. So it's, as I said, it uses the channel an optimal number of times proportional to 1/epsilon², and it's quite simple. It does have some cons though, which is it's not completely simple. In particular, it requires the ability to prepare EPR pairs, and lots of them. And it requires the ability to make these entangled measurements on qubit pairs. So our goal for this talk was to come up with another solution that used absolutely no entanglement at all, no entangled states or measurements or anything, yet which is hopefully almost as good. And we more or less succeeded. So I want to tell you the parameters of our algorithm in some sense. So we came up with an algorithm that uses a tool from this area of learning theory called population recovery. So in outline, it looks like this. It prepares a number of n-qubit states. It prepares m such states, where m is only slightly more than 1/epsilon². It's like 1/epsilon² times the logarithmic factor, log n/epsilon. And each of these n-qubit states is completely unentangled. It's n unentangled qubits. And furthermore, each of these qubits is one of these 6 simple possibilities: ket 0, ket 1, ket plus, ket minus, and ket I and ket minus I. And in fact, these states are chosen completely uniformly at random. So from the 6 to the n possibilities, each of the m states looks like that. You can choose and prepare all those states in advance. And then they're passed through the channel. So we don't use the channel in an adaptive way or anything. We just pass all these states through the channel. And then we measure each of these n-qubit states as they come out. And these are all simple measurements, like in unentangled measurements in the 3 possible bases, the 0, 1 basis, the plus or minus basis, and the plus or minus I basis. And in particular, like, it's the basis corresponding in the output corresponding to the input. So like if you if you prepare a particular qubit to be either plus or to minus, then when it comes out, you also measure it in the plus or minus basis. And similarly for 0, 1 and I minus I. Okay, and then you get mn classical bits of readout. And you do some post-processing that's runs in time mn/epsilon. And finally, you output your estimates, and there will be hardly more than 1/epsilon of them, these p hat sigmas, and they'll have the desired property that with high probability for every string sigma, you'll correctly estimate the probability that the Pauli channel applies it up to plus or minus epsilon. Okay. Good. So it could be, by the way, that these estimates, don't add up to 1. Maybe you'll detect that your channel does all i's, like it does nothing with 80%, and maybe it does an x on the second qubit with probability around 10%, and then the remaining 10% is on like error strings. It's on strings that all have probability individually smaller than epsilon, and so then you don't learn much about them. But as I said, we have the almost optimal sample complexity for this kind of learning target, 1/epsilon². Okay, so I actually put up this slide giving like an overview of how our algorithm looks at a high level. In the remainder of the talk, I'm going to start explaining in detail how parts of the algorithm work. And you should kind of forget what's on this slide for a moment, because I'm going to start saying things that don't exactly seem to match up with what's on this slide. They eventually will match up with what's on this slide, but only at the end. So kind of put this slide, which summarizes the quality of our final algorithm, out of your mind for a moment. Okay, so on to the ideas of our algorithm. And I'll tell you mostly, almost completely, about this first idea, which is a component of the algorithm, which solves a subtask just estimating the probability of a particular string, and like the simplest string, the all eyes string. So estimating the probability that the channel, does nothing to your qubits. So we're going to work for quite a while on just this task. Okay, so again, in thinking about this task, let's warm up by thinking about the case of n equals 1. So there's a 1 qubit Pauli channel, and you're trying to, it does either I, X, Y, or Z to your qubit, and you're trying to estimate the probability of I. Okay, so let's think about what we can do with this channel. So here's our channel. We maybe prepare the state ket 0, we plug it into the channel, we measure it in the 0-1 basis, and it gives us back either 0 or 1. And in particular, if the channel did I, it gives us back 0. And also if it does Z, that leaves 0 unchanged. On the other hand, if the channel does X or Y, then the measurement outcome will be 1. Okay, so we can, if we plug in a ket 0, then we'll tell for sure that, excuse me, the channel either did I or Z, or it did X or Y. Okay, we're trying to estimate the probability of I. So that's some progress, but of course we're going to try plugging in other things as well. And other two things we're going to consider plugging in are ket plus and ket I. And it's easy to check that they have these properties. If you plug in, let's say, ket plus, you measure in the plus or minus basis. Then if the channel does I or X, then you'll get back ket plus. And if the channel does Y or Z, you'll get back ket minus. Okay, and also if you plug in ket I, there's a similar thing where you can tell the difference between I/Y and X/Z. Okay, so that's nice. Now, I'd like to rename the measurement readouts. We have these 3 different kinds of measurements, so they label their readouts different, 0, 1, plus, minus, I, minus, I. But I'd just like to call them 0 and 1. I'm always going to use green for the measurement outcomes. And 0 in this green will always mean like the measurement readout was whatever you put in, and 1 always means the measurement readout was the opposite of what you put in. Okay, so we can summarize it like this. And now our strategy in this n equals 1 case for learning the probability of the channel doing I will just be to do each of these 3 possibilities with equal probability 1/3. Kind of makes sense. I mean, it's a sort of a symmetric situation. And let's understand what happens if we now do this. And actually, there's an important mental shift that you should take now. The way we've been thinking about it so far, I've been talking about it so far, is you imagine that the experimenter, first with probability 1/3 each, chooses ket 0, ket plus, or ket I, plugs it into the channel sort of randomly maybe changes it, we measure it, and so forth. But notice that the experimenter's randomness of doing either ket 0, ket plus, or ket I with probability 1/3 each is independent of the randomness in the channel, whether it does I, X, Y, or Z to the qubit. And let's actually imagine that first the channel randomly decides if it's going to do I, X, Y, or Z according to its probability distribution, but it keeps it secret in its mind. And then the experimenter decides if it's going to plug in ket 0, ket plus, or ket I. So let's just think of the channel's randomness as going first. And if we think about it that way, then something kind of nice happens. So you see, for a given qubit, if the channel decides it's going to do I, which it does with some probability P of I, then regardless of whether the experimenter puts in ket plus, or ket 0, ket plus, or ket I, the measurement readout will always be like 0, green 0, meaning no change, with probability 1. On the other hand, if first the channel randomness happens and the channel decides it's going to do X, Y, or Z, everything is quite symmetric, if you remember from this slide. Then, like say it decides it's going to do X, then there's only a 1/3 chance that the readout will be green 0. That'll happen if the experimenter plugs in cat plus. And there's a 2/3 chance the readout will be like green 1, meaning a change. And that's true for all x, y, and z. Okay, so from this point of view, when you only kind of care about probability of I, and you're not really trying to distinguish x, y, or z or worried about them, you can break things down even further. In fact, in this framework, we're just going to write 0 and 1 for the possibilities for what the Pauli channel might do. And I guess we should start thinking about, we're going to do this, by the way, for all n qubits, separately. So you can start thinking again about trying to estimate the probability of all i's. But since we're only trying to estimate the probability of all i's, we don't care whether a non-I symbol is an x or a y or a z. We just care that it's not I. So we're going to write like blue 0 for i's and blue 1 for either x, y, or z. And so in this way, we have like now sort of a probability distribution p just on binary strings, and we're interested in p of all zeros. And the channel's action is quite classical now. You see that like the channel, if it's going to do like a 0 on a qubit, then you'll see 0 with 100% of the probability. And if the channel does a 1, meaning x, y, or z, on a qubit, then you see 1 with probability 2/3 and 0 with probability 1/3. And this is a very classical channel, like studied by information theorists and coding theorists, that just maps bit strings to bit strings. Confusingly, the classical name of this channel is the Z channel. I don't really want to call it that because it's confusing, like the Z of Pauli's. So a capital zeta looks the same as a capital Z. So I'm going to call this a zeta channel, even though information theorists call it a Z channel. And you can even see why they call it like a Z channel. If you look at this little diagram, you plug in a 0 or 1 on the left, and 0 always goes to 0, but like a 1 can go to a 0 or a 1. But anyway, this channel for bit strings, I'll call it the zeta channel, and it's got what's called crossover probability 1/3. Zeros always stay zeros, but ones have a 1/3 chance of crossing over to a 0. And effectively, we've got a classical task at hand now. There's an unknown probability distribution p on binary strings. We're only trying to estimate p of the all zeros string up to an additive epsilon. Now there's a twist on the learning problem, like when you sort of use the channel and like get a sample, you get like, you don't directly perceive a sample drawn from p. You see like a sample is drawn according to p, which is a binary string, and then it's filtered through the 1/3 crossover zeta channel, and you only see the result of the string filtered through the channel. And actually, this kind of learning task, trying to learn aspects of p despite the presence of this zeta channel, fits into this learning problem framework called population recovery, originally introduced by Wigderson and Yehudayev in 2012, but most commonly studied under the more common classical channels in information theory, the binary symmetric channel, with just like, flips each bit to the opposite with probability 1/3 or some probability, or the binary erasure channel, which just sort of covers up each symbol with a question mark with probability something like 1/3. Okay, so this zeta channel is kind of a twist. It's like a less common channel that people hadn't studied before. But other than that, it fits into this population recovery model. And so we can use ideas from the population recovery literature to solve this task. And it turns out, I won't directly dig things out of the population recovery literature. I'll just say that this channel is not too different from the binary erasure channel. And the fact that the crossover probability 1/3 is less than or equal to half happens to make the situation relatively easy. This is also true of the binary erasure channel. And so I'll just show you directly now the idea you use to solve this population recovery problem with the 1/3 crossover zeta channel. Okay, and that will complete idea number 1, which is how to estimate p of the all zero string up to additive epsilon accuracy. And actually, once you have that, as I'll say, estimating p entirely is also not too hard using ideas from population recovery. Okay, so here's the method that our algorithm uses. It's essentially adapted from prior work on how to estimate probability of the all zeros string when your samples are mediated by this 1/3 probability crossover zeta channel. Okay, so when you get one sample, it's drawn from P, it goes through the channel, and you get a readout, R, which I'll write as R1, R2, up to Rn. This is a binary string of length n. And the algorithm is going to do this funny thing. It's going to compute from this R a real number alpha, which is -1/2 to the power of the Hamming weight of R. Or in other words, -1/2 to the power of R1 plus R2 plus ... Rn. Okay, so this is a number, alpha, between -1 and 1. I mean, I suppose it's actually between -1/2 and 1, if you think about it. But anyway, it's bounded between -1 and 1. And let's spend a little time computing the expected value of alpha. Okay, now there's two sources of randomness, remember, that go into this random variable alpha. So first, a binary string x gets drawn from the distribution P, but we don't directly perceive that. Second, the second source of randomness is x gets passed through the zeta channel, forming this string R, which we do see. And now we're going to form alpha, which is -1/2 to the power of R1 plus ... Rn, which by the law of exponents is also equal to -1/2 to the power of R1 times -1/2 to the power of R2, and so forth. So the key point now is to sort of put yourself in the mind that you're right here after the draw of x, but before x goes through the zeta channel. Once you've drawn x and it's fixed, I want you to observe that the condition on the fixed value of x, these random variables R1, R2, up to Rn are independent. And this is just because the channel acts independently on the n, well, they're bits now, but n qubits originally. And of course, the expected value of a product of independent random variables is the product of the expectations. So maintaining this outer expectation, we can say that the expected value of alpha is the expectation over x drawn from P of the product of these expectations, each of which looks like the expected value of -1/2 to the power of a readout bit, when that readout bit is gotten by filtering the corresponding x bit through the zeta channel. Okay, and now it's not too hard to compute each of these expectations, so let's do that. So let's focus just on any of them, say the first one, R1, and the expectation just depends on what x1 was. If x1 is 0, then the zeta channel always maps 0 to 0. So that means R1 is always 0, and so -1/2 to the power of that is 1, so the expectation is 1, conditional on x1 being 0. On the other hand, if x1 is 1, then the zeta channel 1/3 of the time flips it to a 0, so we get 1/3 times a -1/2 to the power of 0. And 2/3 of the time the zeta channel leaves it at 1, so we get plus 2/3 times -1/2 to the power of 1. And ta-da, if you do this little bit of arithmetic, it shows that the expectation is 0, condition on x1 being 1. Okay, so each of these terms, these expectations on the inside, is either 1 or 0, depending on whether x1 is 0 or 1. And therefore, we can write this expectation of alpha like this. It's the expectation over x, the bit string drawn from P, of the product of like the indicator that x1 is 0 and the indicator that x2 is 0, ... that xn is 0. Of course, this is just the same as the overall indicator that x is the all zeros string. And the expectation of an indicator is just the probability. So in summary, we see that the expectation of this funny quantity alpha that we decide to cook up based on the readout R is nothing more than exactly the thing we're trying to estimate, the probability of the all zero string. And now we're in great shape because we have a nice, unbiased estimator, as they say, alpha for P of the all zero string. And alpha is bounded between -1 and 1. And so like the most basic statistical theorem, Chernoff bound, says that with proportional to 1/epsilon² samples of alpha, if you just draw 1/epsilon², readouts R and form the alpha and average those values, that will be within plus or minus epsilon of its expectation, which is P of all zero string with high probability. And that summarizes how we can learn p of the all zero string to plus or minus epsilon with high probability with, in fact, just proportional to 1 over epsilon squared uses of the channel. And in fact, if you recall, even all the states that we plugged in were just one of 3 possibilities: ket 0, ket plus, or ket I. Great. So that's the end of idea 1. And there are a couple more ideas, but I thought that was the most interesting one, so I'll just go over the other 2 very briefly. First of all, remember, this is actually letting us estimate the probability of all i's, the all i's string. So idea 2 is, okay, that's about estimating the probability of a particular Pauli string, namely the all i's. But idea 2 is actually for any fixed length n Pauli string sigma of your choice, a very similar algorithm will allow you to estimate it up to plus or minus epsilon with high probability. And it's just a little twist. You conjugate your inputs and your outputs, something like this. And that lets you learn based on sigma, and that lets you estimate p of sigma. And this is why the actual overall algorithm doesn't just use ket 0, ket plus, and ket I in the input. It actually uses all 6 possibilities: 0, 1, plus, minus I, minus I. Okay. So this thing, the ability to do this second thing, is what's known as individual recovery in the literature on population recovery, the ability to estimate one particular string value. And population recovery refers to estimating all of them up to plus or minus epsilon simultaneously. But there's a well-known idea and algorithm in population recovery that reduces it to individual recovery. So we just basically straight up borrow this, and it's a pretty simple idea. I'll just say, like, in a few words how you use it. Basically, stage 1 is you ignore all qubits except the first one, and you learn p of I, p of x, p of y, and p of z on the first qubit. These are like the marginals in the first qubit. Okay, and that's 4 separate problems that you estimate up to plus or minus epsilon. And then, if any of these marginals has probability like less than epsilon, you can discard it because all the extensions of those marginals will also have probability less than epsilon. And then you try to extend it. You try to learn the marginals on symbols 1 and 2, and on symbols 1, 2, and 3 for a bunch of prefixes. And you never keep around more than about 1 over epsilon many prefixes, because you only keep around a prefix if the associated marginal has probability mass at least 1 over epsilon. Okay, and you do that, and you make your way all the way to learning probabilities of entire strings, the heavy ones that have probability at least epsilon or so. Okay, and you have to use the union bound a bunch of times, and that's why we get this additional sample complexity factor of log n over epsilon. Okay, so that's more or less all I wanted to say about the algorithm. We put some more bells and whistles in there about a little bit about tolerating, measurement noise and getting multiplicative approximation factors rather than additive ones, and a Fourier analysis perspective that connects the problem to Goldreich-Levin algorithm. But for all that, you can take a look at the paper. So I'll just summarize the main highlights of our algorithm. As I said, it prepares a number of n-qubit states that are completely unentangled. The number is only a logarithmic factor more than the information theoretic minimum, 1 over epsilon squared. You prepare all the states, pass them through the channel, measure them unentangled fashion in the obvious basis, do a little bit of classical post-processing, and overall, you learn all the Pauli error probabilities up to an additive epsilon with high probability. Okay, that's it. Thanks for listening.